The PPT is shared, right?
Yes.
Okay. So motion. So motion refers to change in displacement, with respect to time. Whenever there is a change in displacement with respect to time, the parameters that are involved in understanding this is what you will study in motion. So the parameters involved here is displacement, distance taken place, velocity, speed, or maybe I can say speed and direction, the change in direction, change in velocity, or what you call as acceleration. So all these parameters comes into motion. So we are going to see about how each one of these parameters change when the displacement of the particle changes. So towards it, there are two types of motion we look into. The first type of motion is called as uniform velocity motion. The second type of motion is called as non-uniform velocity. Sometimes we also call this as constant acceleration. Constant acceleration. So here, broadly, if you want to classify, you can say something like this. And if you still want to classify non-uniform, there are two ways once again. The first one is non-constant acceleration. The second one is variable acceleration. Variable acceleration. So this is how the entire mind map for this goes across. In fact, I had to divide it like this over here. Then it makes sense. Okay, the same thing I put it over here. So this is how we have, and of which we'll be studying in detail about uniform velocity, and then we'll be studying even about the constant acceleration, a equal to constant. But this one we will not be looking into it because variable acceleration means there's a change in velocity every time. There's no pattern being observed. So wherever there's a pattern observed, we are going to look into it. So these are only two things that we are looking into. Okay. Now let us look at distance. Distance traveled by a particle is what you call it as a path length. Path length. For example, a particle starts from point A here. It goes like this and it reaches this point over here. So if I want to find the distance, what I need to do is I take a thread, put it across here, fix it across here, then pull it across in the same direction. And then I find out what is the length of the thread over here. If you now stretch the thread will start from here and might go until here, which means now this is the total path length what I have found out. The next is about displacement. Displacement is nothing but the shortest path between 2 points.
Yes.
So as a result of this, you take this point A, which is your initial point, take this point B, which is final point. Now you just join a line connecting this point A and point B, and this will be your displacement. So as you see, when a particle moves in a curved path or not in a non-straight line path, then in that case, the displacement will be lesser than distance. This is one thing which we can say here. Now, if I look at the properties of distance can be equal to 0, it can be greater than 0. Displacement can be equal to 0, less than 0, and greater than 0. Because displacement is a vector, while distance is a scalar. It does not have any direction. When I say distance is equal to 0, that means position of the object has not changed. Or you can just say the object is at rest. While when I say displacement equal to 0, you can say the object is at rest, object returned to the same point. So this is what we can say. A particle starts from here, goes here, and again comes back down. So this is nothing but your object returned to the same point after a finite interval of time. So then you can say displacement equal to 0. Thus, whenever we talk about displacement, we have to be very careful. But in case of distance, this is what it is. And the distance can never be negative. One important point which we need to look at here is that distance is non-negative. Is non-negative. But displacement can be negative, can be positive, depending upon which direction it has been moving. A particle starts from point O, the particle starts from point A here, goes to B, and maybe it again comes back like this and reaches the point C over here. And if I ask you what is the displacement here, displacement is nothing but the distance, the final distance between point A and point C. The shortest distance between them is your displacement. So therefore, this can become negative. This can become negative provided that this is my origin. So this is my positive x-axis and this is my negative x-axis. So as a result of this, this can become negative. So this displacement can become negative, but when you ask about distance, so you have to count the whole distance here. It went until here, okay, and then it came back once again and reached the point C. Whatever path it has taken, that will be the total distance, which will not be negative once again. It will only be positive value. So negative values also have to be flipped to consider that as positive. That's what is the difference between the distance and displacement. Okay, the next is, so we have seen what is distance, what is displacement. Let us look at velocity. Velocity and speed. If you have any doubts, you ask me in between.
Yes.
Okay, velocity and speed. In velocity, velocity is nothing but velocity is equal to displacement divided by time taken, while speed is equal to distance by time taken. Speed is a scalar, while velocity is a vector. Speed can be 0, can be positive. Vector can be 0, positive, or negative. Now let us look at the implications. The implications here is that when I say a particle is moving, a particle moves, and if you ask me after a certain interval of time what is its velocity, then I can now answer velocity in terms of 4 parameters. The first parameter is, you can say, what is the initial velocity? Initial velocity, okay, I'll come back to this problem once again. Okay, initial velocity u is nothing but velocity at time t equal to 0. The final velocity v is nothing but velocity at a given destination. At a given destination. And then you have average velocity. I'm only talking about velocity here, not about the speed. Speed, I will write it here separately. Then average velocity, this gives me the net displacement divided by total time taken. Remember, this is not u plus v by 2. You cannot use that here. You have to just use net displacement divided by time taken, because u plus v by 2 is applicable only under one circumstance. When we come to acceleration, I'll tell you about this. So you have initial velocity, you have final velocity, you have average velocity. Then we have instantaneous velocity, which is v of t. We generally call this. This will keep on changing. This will keep on changing. And most of the time, this instantaneous velocity is nothing but the final velocity. Okay, because velocity at a given destination means the destination it has arrived only at a given unit of time. So therefore, you can also say that this will be your instantaneous velocity. Okay, now let us look at the values of u, v average, and v instantaneous. Now towards it, if I look at the value of u can be 0, u can be less than 0, u can be greater than 0. U can be greater than 0. Can you tell me when can u be 0? I'll write it here itself.
So when the object,
Sorry?
when the object,
When the object is dropped.
yes, or it starts from rest, like
Starts from rest.
parked and then it starts moving.
Yeah, it starts from rest or it has been dropped. You can take u equal to 0. u greater than 0 means, what does it tell you? U greater than 0. I say that the object has a velocity of an initial velocity of 3 meters per second. What does it tell you?
U greater than 0 means it's already started moving.
It has already started. That means it has started at point O here, and you are standing here keeping a timer with you, and you started the timer, okay, when the object crossed you. When the object crossed you, the velocity at this point was u greater than 0, which was at t equal to 0 here. Because you are counting the velocity only at t equal to 0. So this is u greater than 0. When u less than 0, what do you mean by that?
So u lesser than 0 means it's then now it's like in the coordinate system. You need to look at it like that.
Yes, it's in a coordinate system. You are standing here at the origin at t equal to 0, and you observe that the particle is already here, and it has started to move here. Okay, it is starting to move, or it's already moving, and you counted the timer at this location. Let us say this location is at a distance of 1 meter, and you found out that the velocity is like this, but its direction is in the opposite direction, because for you, the coordinate at t, you say this is your positive direction. So therefore, this is how the u be equal to 0, greater than 0, and less than 0, you count. Then, now let us come back to v. V is nothing but the final velocity. Final velocity again can become 0. What do you mean by final velocity becomes 0? When do we have final velocity to be 0?
When the object in the end.
When the object stops. When the object stops, okay, so you dropped a particle from a certain height, the object came to the ground, it stopped here.
Yes, that's where v is equal to 0.
Yeah, so it landed onto the surface. You can say stopped. V greater than 0 and less than 0 follows the same terminology as what we had seen here. So therefore, so this is your final velocity. Final velocity also can take up any values. And then comes the average velocity. What is average velocity? Average velocity is net displacement by net time taken. So therefore, this value can also take 0, less than 0, and greater than 0. All of them it can take. Now, when do we say when it is equal to 0? What do we say when it is equal to 0?
When it's equal to 0, so
Yeah.
basically when it's come back to its starting position.
Yeah, which means the net displacement is equal to 0. In that case, you can say the average velocity is equal to 0. Net displacement equal to 0. At no other point you can say average velocity is 0. If the particle is moving in a straight line, it doesn't turn back, then definitely the average velocity cannot be 0. Or the average velocity can now be an acid test for you while you are investigating problems, saying that, okay, whether the particle has turned back or not. If the particle has not turned back, then quite might be the particle is just moving in a straight line, but still, okay, it can be greater than 0, but it could have turned or it could have had turns over here. Okay. And then I'll come back to one more case over here. And then we have seen we have a instantaneous velocity. It's nothing but the velocity at a given instant of time. So it keeps on changing with respect to time. If it does not change, let us say if v of t is equal to 0, what will happen? What do you mean by that? If instantaneous velocity is equal to 0, what do you understand by that? What's happening to the particle?
So that means at that instant, the particle is at rest. At that time, instant t.
At that time, the particle is?
At rest.
At rest, okay. If v of t is equal to 0, this is what happens. If v of t is less than 0, it means, what do you mean by v of t less than 0? Is it the velocity is reducing? Is the
No,
velocity reducing, increasing? Yeah.
not going in the same coordinate direction.
Yeah, it is going the opposite direction. That's it. Okay. When you have difference in velocities, delta v to be less than 0, then you can say that the final velocity minus initial velocity is less than 0, and you can talk anything about it. Okay. But while if you have delta v, if you just have absolute value of v to be less than 0, okay, so it only means that there's a change in direction. It is moving in the opposite direction as compared to the positive coordinate. That's it. Okay, so we have seen all these parameters. Somewhere I thought I should explain something here. when it is V average. Okay, let me come back to it once again. Okay, now we have seen what is velocity at every point here. And now let us look at speed. In speed, we have speed, initial speed. It follows the same letters. Initial speed equal to 0. What does it tell you? Initial speed of the particle is 0, which means
So that means it starts from at rest, right?
the particles started from rest, are being dropped. You can use all these terminologies. The final speed is equal to 0. Again, the same thing, but no direction. So equal to 0, less than 0, greater than 0. All this means the same thing as what we had seen there. Because this final velocity and instantaneous speed, both of them will mean the same when we consider the particle moving. And the next part is V average. It is very important to note here. In case of V average, this will never be equal to 0. That is, the average speed cannot be equal to 0 if the particle was moving. If the particle had moved. If the particle had moved, definitely the average speed cannot be equal to 0. And then the V average cannot be less than 0 also. Okay, whenever the average speed we are considering, it cannot be equal to 0 or it cannot be less than 0. V average cannot be less than 0. V average should always be greater than 0. Now,
Yes.
let us see why does it happen like this. V average is defined by, that is the average speed is defined by, total. Now I am replacing displacement with distance divided by total time taken. As a result of this total distance, now let us say I take a particle here, it starts from this point, it goes over here. Let me say this is point O, this is point A. Then from here, okay, let me say this is distance is S1, this time is T1. It starts from here and reaches another point here, point B. This is 2S1 and this is T2, or maybe this is T by 2. I do it something like this because I want to simplify things. And then what I do is I again return back like this and reach to the point over here. And the time taken here is, let us say, 3t. Let me just take S and T itself, not S1 here. Yeah. Now, based on this, if I want to calculate what is the average speed, if it was average velocity, directly we can say the particle started at O, it went through all this and again came back to here. So the average velocity was 0.
It's actually like a y component thing. The height is different, right? So
Uh, y component, why are you getting that y component here?
like y, so because there's a y displacement for O, because it's ending down
Oh,
below
I'm
O.
sorry. Okay, no, I am not looking at y component here. It's not a two-dimensional motion. It's a one-dimensional motion. It goes over here because I didn't have enough space to write it, so I written it below it. Okay, so I am not saying the particle has got displaced by this amount. I'm saying that the particle started from point O, went to point A, point B, and again retracked the same path. It went like this and reached the point O once again. So that I have described it like this. Is this clear?
Yes.
Okay. Now towards it, if I want to find what is the average speed here, this will be total distance will be S plus 2S, 3S, and when you're returning back, it's again 3S, which would be 3S plus 3S, which is 6S, divided by total time taken. Total time here is T plus T by 2, 3T by 2, 3T by 2 plus 3T, 3T by 2 plus 3T, which should now be equal to 6S divided by 2 3s are 6 plus 3, 9, 9T by 2. 3 ones, 3 twos are, 3 threes are. So now this should be equal to 4s by 3t. Okay, 4s by 3t. So therefore, this is what is my average speed here. So thus the average speed here is not equal to 0. So even though the particle returns back to its original position, you have to use only this formula over here. Right. Now, under what conditions can we have the initial velocity, final velocity, average velocity, instantaneous velocity, all of them to be equal? Is there any kind of motion where all of them are equal?
So actually we can if an object doesn't move at all.
If the object doesn't move at all, okay, you mean it has to be at rest. Okay, then any other condition? Apart from this,
Um,
the object is moving, but still all the 4 conditions are seen to be correct.
I don't think that's true because we have this thing v of t, right? Because instantaneous velocity is also there, therefore it's not true. Otherwise, we can have lots of cases.
If a particle is moving with the same velocity at all times, then what can happen? Let us say the particle, you started the timings at t equal to 0, and you found out at when the particle crosses your timer, it is at 3 meters per second. It's moving with uniform velocity. It's moving in a straight line. It's not returning it or it's not moving in a curve. So at t equal to 0, it was 3 meters per second. At t equal to 5 seconds, if you watch what is it, there's no friction. So it is still moving at 3 meters per second only. Am I right? There's no external force acting on it.
Yes.
And when you look at V average, again, what is V average? The total displacement divided by total time taken. Okay, so there also you will get the same one. V average will also be the same. Are you able to understand this? How is V average the same? And instantaneous velocity, by definition here, it will also be the same. Are you able to get this one?
Yes. The uniform motion.
Uniform motion. So therefore, so this result will also be true when the particle is moving with a uniform velocity. Okay, it's not uniform speed, it is uniform velocity over here. Now, can you tell me what happens to this in case of a uniform circular motion?
Velocity is changing at every point, sir. It's only the magnitude which is remaining the same.
Okay, but with the parameters, which parameter do you think will change? Because I'm not measuring direction anywhere here.
V of t, so V of t will change.
Sorry?
V of t.
V of t? V of t will be the same because everywhere I'm moving in a circular path, it should be 3 meters per second only.
I think V average, right, sir?
Yes. All this will remain a constant, will be the same. But this will change because what happens is u will be like this over here, and here it will be like this over here. This will be your u, this will be your v. And if you ask me what is the average velocity calculated over the point A and point B here, what I will do is I will not consider anything. I'll just consider this chord here. This chord will now be equal to, this will be your radius r, this will be another radius r, this will now be equal to r root 2, right? R square plus r square is r root 2. So r root 2 divided by the time taken for it to go. Okay, the time taken, what I can do is I can again write this as r root 2 divided by 2 pi r by v, because it's the speed, right? The total distance traveled is 2 pi r in one circle, and v is nothing but uniform velocity. This r also goes away. So I can now write this as v by root 2 pi. Is this clear?
Yes, sir.
So this will be the velocity here. Okay, so this will be your V average. So V average is definitely not equal to 3. It will be 3 by root 2 pi. It will be lesser than that. Okay, so we have seen speed. We have seen how does the speed changes. Okay, and which parameter actually changes? This parameter, V average, actually changes. Okay, so now next thing is, let us move on to acceleration. Acceleration. Acceleration is nothing but change in velocity divided by time taken. This is nothing but your vector A. And I say that this is a vector A, the reason is because this acceleration changes whether there is a change in velocity or there is a change in the direction of the velocities. For example, a particle starts from point A, it moves to point B. The velocity at this point was, let us say, 3 meters per second. The velocity at point B is 5 meters per second. And this change in velocity took place in 4 seconds. In that case, I say that the acceleration here can be written as 5 minus 3 divided by 4, which will be equal to half meter per second square. The unit is per second square, meter per second square. But now, let us say the particle is not going like this. The particle moves from here to here. So point A, point B, this took 4 seconds from here. This is at u equal to 3. And let me continue with the same speed. Let us say, for example, here v is also equal to 3 meters per second. Then it took a right turn here. And while it took a right turn also, it moved at the same speed once again. And it reached the point C here. Okay, see, I'm not changing the speed here. The speed is same, but the direction I am changing here. Here, the direction was same, but the speed was changing. There's a difference between these two. So here, when it reaches the point C also, I observe this speed is also seen to be 3 meters per second. So everywhere, the same speed has been observed, but the direction has been changed. Does it have an acceleration? Does a particle experience an acceleration?
Yes, it does because there's a change in direction.
Yeah, so there it experiences an acceleration. How do you calculate the acceleration now?
You have to use vectors and then do the differentiation of the velocity, sir.
Differentiation, there is no parameter like Tx here. I have given you already constant values.
Yeah, so actually everything constant, right?
Yeah, so acceleration is not there.
Yeah, magnitude is zero.
Magnitude is zero. So there is no acceleration, which means?
No, so but there's a direction. No, you can have a zero vector. So basically it has no magnitude, but there is.
There is an acceleration, right?
Yes.
Okay, let us calculate what is that acceleration here. So as I said, acceleration depends on these two. So acceleration, as by definition, it is given by vector v minus vector u divided by t. T is a scalar. Okay, so this division is possible because you are just dividing it by a scalar, which is nothing but 1 by t times so much. So it's just a scalar multiple here. Okay. Now v, what is vector v? This is my vector v. So I will first write the line vector v like this. And then vector u is in this direction. Vector u is like this. But since I have vector minus u, I will write the line minus u like this.
Yes.
Then when I say vector v minus vector u, this I can write this as 1 by t multiplied by vector v plus minus vector u. I can write something like this. That means I'm going to add these two vectors. When I add these two vectors, one vector is going to be like this. The other vector, I'm going to take the tip of this, join it with the head of the other one. This is my v vector. So sum of these two, okay, by triangle of vector addition, I can write it like this. So therefore, this looks like a right angle triangle for me, and hence this is 3, and therefore this should be 2 root 3. Am I right? 3 square plus 3 square is equal to r square. Then 2 into 3 square equal to r square or r. Oh, I'm sorry, it is not 2 root 3, this is 3 root 2. Correct?
Yes.
Okay, this is 3 root 2 here. So I got the value of 3 root 2 here. Thus the acceleration does not become 0, and this becomes 3 root 2 divided by whatever time it has taken. Okay, let us say here it takes 2 seconds and here it takes 2 seconds. So therefore, I will write these two, and thus I'll add this as divided by 4 seconds. So this will be my answer for acceleration here. Okay, thus acceleration exists whether the particle's speed changes or whether the particle's direction changes. In both the cases, there will be an acceleration. But in case of velocity, do we have the same thing in case of velocity? Can we arrive at a similar expression in case of velocity?
Yes, we can have just direction.
You cannot have with respect to the direction,
With velocity.
Yeah,
With velocity, I think you can, right, sir?
you have to. Okay. So let us say, for example, a particle starts from this point, again goes here, and it takes a turn like this. And you ask me, what do you ask here? You say that it is a change in position versus time taken. So let me call this vector as vector r1 and this vector as vector r2. Okay, vector r2 is like this. Vector r1 is like this. Then what is your velocity here? If you say what is your velocity, then what you need to do is v is equal to r2 minus r1 divided by t. Now what is r2? R2 is in this direction, r1 is in this direction. So you get it like this, or you write it like this over here. Okay, so as a result of it, your velocity will be directed in this direction. Did you understand this?
Yes.
Okay, so therefore, so we write it like this. We don't call this as just velocity, we call it by a new term. The term which we call here is called as resultant velocity. Okay, but this is not very much significant over here because we would be more interested in understanding the instantaneous velocity or the average velocity, and that is the reason why this term often gets masked. Okay, so we do not use it because there's one more place where we use the resultant velocity, wherein you have a particle, it is subjected to two different velocities like this, and now you ask the question, where is the particle going? You say the particle is going like this, and this you call it as resultant velocity there. Okay, so as a result of this, so this particular thing has been masked. We don't use it much. So we only speak of those four velocities which are sufficient enough for us to quantify the direction and as well as the magnitude of the motion. And average velocity dominates this one to understand about, okay, so how do we quantify or how do we summarize the velocity? If the velocities are changing often. Is this clear?
Yes.
Okay. So we have seen speed, we have seen velocity, we have seen distance, displacement, and now we have seen acceleration also. Now what is that we need to do? Okay. The next is, okay, we have seen average velocity also, right? Okay, let us start with the equations of motion. As I had already suggested that when you have a particle, the motion of a particle can be divided into two parts. One is uniform velocity. The other one is uniform acceleration. If you want, you can put one more criteria here, which you call it as non-uniform acceleration. So when you want to use uniform acceleration, which means the value of the acceleration is predefined, and you can say this value is equal to something like 3 meter per second, 7 meter per second, 22 meter per second square, and so on. Not meter per second square, and so on. Then you call it as a uniform acceleration. When I say the value of the acceleration a is equal to 0, then comes uniform velocity. Now here, non-uniform acceleration, when you say the acceleration a is equal to 3 times t, which means as you vary the value of t, the value of acceleration also changes. I can also say it is something like 3 times x or 5 times x, 5 times x or 5 times x square. So if you have a variable associated with an acceleration, in that case, you can call that as a non-uniform acceleration. In all other places where the acceleration is expressed in terms of a number, you can call it as a uniform acceleration, which is a constant value. And when that constant value is equal to 0, you get uniform velocity. And if it is associated a number, a coefficient with a variable, then you call it as a non-uniform acceleration. So this variable can be anything. It can be time, it can be speed, it can be velocity, it can be displacement, distance, square of distance, it can be anything over here. So this is what you call as non-uniform acceleration. Whenever you have a uniform velocity, now let us look at uniform velocity first. Uniform velocity, a is equal to 0. And then as I said, the only parameter that we have is it's moving with same speed. So your uniform initial velocity, final velocity, average velocity, sorry, not average velocity, initial velocity will be equal to the average velocity will be equal to the instantaneous velocity. So there is no point in discussing these three things separately. And as a result of it, there's only one equation that we have. That equation is, how do you find velocity? The simplest answer is velocity is equal to displacement divided by time taken, nothing else. Okay, which I can now write this as x by t or x equal to ut. This is what we can say. You can also write y equal to ut also. And this x or y tells me in what direction the particle is moving. If the particle is moving along x-axis, I use this. If a particle is moving along y-axis, I use y here. Okay, and then yeah. Okay, let us say, for example, the particle is moving like this, which is making an angle of 60 degrees. Now, how do I write an equation for this? Now, this is moving with an uniform velocity. of, let us say, 7 meters per second, a particle is moving in this direction. Now, can I write an equation like this, or should I change my equation? This is my x-axis. This is my y-axis.
Yes.
Yeah. So how do you write this here?
So what you can do is you can do the components now, I guess.
You can do the components.
Put it in
If
I and J form.
Okay. So which means you want to write 7 cos 60 along this direction and 7
And
sin
7
60
sine 60, yes, sir.
along this direction. Now this is a not
So
under
you get,
gravity. Yeah.
so you get 7 by 2I
Yeah.
plus 7 root 3 by 2I.
Yeah. This is what you will get over here. But my question is that is it moving under uniform velocity along both x and y direction, or is there a difference when I split it like this?
So it'll be the same, sir.
That means the uniform velocity will be seen both along x and y axis.
Yes, sir.
Right. You will be seeing two equations. That means you are complicating the motion. But if you ask me how to do it, I will say, consider this as my x-axis. I'll shift my origin and say, this is my new x-axis. I don't want to consider this at all. And then I'll directly say that displacement can be written using this equation. Isn't it quite clear? Is it not easier?
Yes, sir.
This would be easier. In physics, we are allowed to change the axis. Okay, but you should be consistent about changing the axis every time. Okay. Now, this is only one equation that you have for uniform velocity. So one of the easiest problems that we have. The next comes your uniform acceleration. Uniform acceleration. In a uniform acceleration, we say that the a value is not a variable quantity, a equal to constant, which means that if I write a equal to constant by basic definition, I can now write a equal to v minus u divided by t, or you can now write v is equal to u plus at. By transforming, by pushing this way, you get v equal to u plus at. What is this expression? This is an expression for velocity or acceleration. What is it?
So this is for final velocity.
This is for
Final velocity.
final velocity. And what about the instantaneous velocity equation?
So instantaneous will just be, you find the displacement from the origin and you differentiate that.
Not necessarily. This is also your instantaneous velocity. Instantaneous means this velocity is a function of time. Right? At every instant, the velocity changes, and that's what is your instantaneous velocity. So instead of writing v, you can also write v of t equal to u plus at. Is this clear?
Yes, sir.
Okay, so velocity, final velocity and instantaneous velocity are one and the same here. There's no change. Okay. Now we have seen uniform acceleration. One of these equations is the first equation of motion. The second equation of motion is that now what we'll do is we'll consider, okay, okay, I want to just wait. Let me write the average velocity expression here. No, not average velocity. Just wait. I need to give you some in-between link. I'm just thinking of it. Okay, let me start with this. Now what we will do is, let us say, we'll square this. When we square this, you get this as v square equal to u plus at the whole square, which will be, if you expand this, this will be u square plus a square t square plus 2u at. Let me call this equation as equation number 2. Then what we do is, we know that v minus u by t is equal to a. The average velocity when the particle is moving with uniform acceleration can be written as u plus v divided by 2 into t. See this, sorry, not t, sorry. U plus v divided by 2. See this expression, we can use it only when the particle is moving with uniform acceleration. When the particle's acceleration is changing, you should not use this. Is this clear?
Yes, sir.
Okay, so average velocity can also be computed using this. Okay, provided the acceleration is constant. Okay, now towards it, now we have um, now we have so much. Now we can also, okay, let me take up a new slide. Yeah, we can take up a new slide to derive the equations of motion. So we have already got V equal to U plus AT, and then we have V average is just a moment.
Yes.
Can you call me back after 5 minutes? Hello? Yeah, I'm in a classroom now. Do one thing, do send me the report. Yeah. Not an issue. Okay. I have given the marks. Yeah, now it can't be changed. Yeah. No, that has been fixed. It's difficult now. Okay. Exactly. Hmm. Okay, fine. Now call me back after 9 o'clock. We'll discuss about it. Not an issue. Yeah, I'm outside. Okay, I'm back. Just a moment.
Yes.
So V average. Okay, V average is given by U plus V divided by 2. And the distance traveled by the particle with an average velocity is given by U plus V divided by 2 into time taken. How did we get this? This is a total distance by total time taken is nothing but V average. So as a result of it, I just flipped or I just cross multiplied it. So you get V average multiplied by T. Okay. Now what we do is in this equation, okay, this is my first equation. The second equation, what I do is I substitute from here, I substitute it over here. I'll write this as U plus AT divided by 2 into T. I'll keep this one aside. So yes, should now be, hello. Hey, तो ये कर लिया इन्वर्ट कर गया हेलो
Hello?
I think I lost my connections in between. Yeah, just a minute. Let me reshare.
Yes.
Okay. So we have substituting this value. What happened to this? This should become 2u plus at divided by 2 into t, which should now be equal to u plus at by 2 into t, which should be ut plus half at squared. So thus, we are able to arrive at the second equation of motion.
Yes.
And then let us look at the third equation of motion. The third equation of motion suggests that we will take up from here v equal to u plus at, square this, which will become u square
Plus 80
square
square.
t square plus 2u at. And then I will take u square outside. I'll take u square here plus I will take at outside, or a I will which of them can be common? At can be taken common.
Yes, you can take 80 common and you'll be left with 80 plus 2u.
Now instead of at, what do I need? I want v square equal to u square plus 2as. So I'll take 2a common outside, so that this becomes at square by 2 plus 2a common inside, it should be ut. So from here I can substitute and I can write this as u square plus 2as. This is my equation 3. So therefore we have got all the three equations by equation method. We are assuming something while we do these expressions. Can you tell me what are the
Acceleration
assumptions?
is constant.
Sorry?
Acceleration is constant.
Acceleration is constant, and then there's one more.
That's the most important assumption we make, right?
No, the first assumption is right. There's one more assumption we are making.
That there is an acceleration.
Yeah, that is what. Acceleration is constant. That's what we are assuming here. There's one more here.
Not sure, sir.
The particle at t equal to 0 is at x equal to 0. Okay, if this assumption fails, let us say at a time t equal to 0, the particle was at x naught. It's something like this. This is your timer at t equal to 0. You're standing here at the origin. The particle is here, and later on from this point A, it is moving with uniform velocity. Okay, so it's moving, so not it's moving with uniform acceleration. Okay, now what modification do you think will happen here in any one of these equations? Where does the modification change? Where does it change? Yeah. If the particle starts not at the origin, but at a different point, where do you think? Okay, here I've used S here, right? Let me choose this as at s equal to 0. I'll choose this as S here and choose this as S naught over here. S naught here. Okay. Now, where do you think, which expressions do you think the modification will happen?
In S, sir.
Yes, it will change. So therefore, this expression will become S minus S naught is equal to ut plus half at square, or you will write S equal to S naught plus ut plus half at square, which tells me at t equal to 0, S was at S naught. In a similar way, here also the same thing happens. You have to replace this S by S naught, S plus S naught. 2as plus 2s S naught. So you will get v square equal to u square plus 2as plus S naught. There's a bracket here, 2a into S plus S naught. Is this clear?
Yes.
Okay, so we have seen equations of motion derivation from the first principles using equation method. Now let us look at graphical methods. Just a minute. Graphical method. Now, before going into graphical method, we need to understand what are the types of graphs. Okay, so let us look at the types of graphs. The first one is my ST graph. What are the variants of ST graph? Let us look into this. Now, ST graph tells me there are two types of ST graphs when S stands for distance and S can stand for displacement. Now, let us start with the distance time graph. Distance time graph. Now, towards it, if I have a distance time graph like this, what does this suggest me? The distance is seen to be a constant with respect to time. What does it indicate? Let us say the distance here is 5 meters. Sorry?
Object is at
Object is at rest. Okay. And then what else can it say? What does it say? What does this 5 meter indicate? What does that y-intercept indicate?
So that it's 5 meters from the origin.
Yeah, it's 5 meters from the origin. So I am standing here. The particle is standing at this point. At t equal to 0, I observe the particle is here. Okay, and it does not move. So this is what is the 5 meter. Now let us take up one more graph. This is t, this is s. Right. Now this is one more graph. Now what does this tell you? This is 10 seconds. This is 5 meters. Is this correct?
Yes, sir.
This is correct. Okay, tell me what happens then. Remember, we are talking about distance time graph. So my first question is this graph possible or not possible?
This is actually possible here.
This is possible? Can the distance decrease with time if it is moving?
Distance, no. So distance cannot.
Yeah, that's what I said, distance time graph. So this graph is impossible. Okay, now let me draw one more graph. Now, wait, I have not completed this. Yeah, now this is point O, point A, point B, and point C. Yeah, is this distance graph possible or not possible? Is it possible? Yeah.
No, sir, that's actually not possible.
Why is it not possible?
You're going back in time, sir.
Yeah, we are going back in time, so therefore, what has happened to this? Okay, they are going back in time, so this is also not possible. Okay, if suppose instead of the graph going back like this, if it was coming down like this, because we are proceeding in time. So is this possible? Start from O, go to A, point B, and then D, instead of going back to C. So this part of the graph was not possible, okay? Because it was going back in time. What about this graph? OABD. Is it possible?
That is possible, yes, sir.
This is possible. Again, distance time graph. Look at this BD. Isn't this BD similar to this point, this line? Which means here the distance is increasing, And here you see the distance went to a maximum and all of a sudden it is decreasing here. Do you think this is possible? The region BD is possible?
No, actually, even that's not possible. So it
Yeah,
can't go
this is
down.
also not possible. Okay.
OAB is possible, but
AB is
after
possible.
that,
Yeah, OA is possible, AB is possible, but BD is not possible. Okay, let me do one more graph. Wait. Okay.
so again, it's going back in time.
Yeah, so therefore, now here you see for a given time coordinate, there are two displacements, which is impossible. Sorry, two distances, which is impossible. Okay, so this is also not possible. It's again going back in time. So it comes here. So first of all, it goes back in time. So you cannot reduce it like this. So this is also not possible. Okay, now let me give you one example. I have been giving you graphs and asking you situations. Now let me give you a situation and then ask you to draw a graph. Okay. A pendulum is oscillating. How do you draw a distance time graph for the pendulum's bob? The amplitude of oscillation is A. The amplitude of oscillation is A. Yes. Now, how do you draw the distance time graph for this? Okay, let me again specify this. I will say that I want you to draw the distance time graph for the particle's motion along the x-axis. Why did I specify this? I just didn't say you the same thing initially, but now I specified that the particle's motion along the x-axis should be drawn. Why?
So that's because along the y-axis, it goes up as well. There's a two-dimensional motion.
Yeah, the motion is a two-dimension. Now we need to look only at the one dimension here. You have studied this already.
So is it just it won't it just be an oscillating thing?
Yeah, it's an oscillating one. But I want the distance. I don't want the displacement here. You just ask the question, in what time? Okay, let us say it starts from here. It starts from here. In a time t/4, it travels this distance. It travels a distance A. Okay, in a time t/4, let me consider for a given time period t. This is t/2. This is t/4. In a time period t/4, it travels a distance A. This is my distance A. This is my distance 2A. This is 3A. And this is 4A. So in time t/4, it travels a distance A. And then what happens? In the next time period t/2, what happens here? It travels a distance 2A, right? It starts from here, goes in a time t/4 here. By the time it reaches here, the time taken is t/2, and it has already traveled a distance of t/2A. Am I right? The displacement can be 0, but the distance traveled is
Yes.
A plus A.
Yes.
And similarly, if I take 3t/4, the point is here. And if it is complete t, the point is here. Now there are 4 points. Do you think that I should draw this by a straight line? If it was straight line, then definitely it means that S by T is a straight line. It moves with uniform speed. But is that happening?
No, so it doesn't move at uniform speed.
It doesn't move with uniform speed, which means what kind of How should I draw these points? How should I join these points? It should not be a straight line. It should be a curved path. Am I right?
Yes.
And how should the curved path be? Should it be like this or should it be like this? This is 1, this is 2. Which one is the right one?
I think
First
one
one
is right.
First one?
No, second one.
Second one is the right one. What is the reason?
So because it increases, it increases in that manner. So it's like it increases upward, not in the
Why?
like that.
Why do you say it increases upwards? Why not downwards like this? So you will get a graph like this, but you have to reason me why you get a graph like this.
When you draw it and then you plot the points, so that's how it will be.
Sorry?
When you plot the points, right, that's how you will get
No. Okay, that is experimental part. That I'm not worried. But theoretically, you have to reason now.
So when it goes from the mean position to this thing, it first goes to the maximum position and then comes back to the mean position, or to any of the amplitudes.
Now what happens is, see, when I say s equal to 0, this was s equal to 0. The mean position was s equal to 0, right? At this point, the velocity was maximum. And then it started reducing its velocity. When I say velocity is maximum, s by t, that is, if in a st plot, okay, the gradient of it will give you the velocity, which means if I have a curve like this, the gradient of the slope will be this line. This line, the slope will be 0, which means the velocity at this point is 0, which is not possible. Okay, which is not possible. But on the other hand, if it was like this, then you see that this will be the velocity here. The tangent at this point is velocity so much. Maybe it's not vertical, maybe it is slanted like this. The velocity is very high here because slope is now nearing to y-axis. So the velocity is very high. But as it keeps on going, you see the velocity becomes 0, nearly lesser. And when it reaches this point, I will show this by a plateau. Okay, when it reaches this point, the velocity becomes 0 here. And from here, again, it starts like this and it becomes like this. So therefore, you will get a curve like this. Is this clear?
Yes, sir.
Okay. So therefore, you should get a curve like this. It again depends upon, it's the same thing, yeah. Yeah, we have seen a pendulum, we have seen an ST graph, distance time graph. Anything else I have left out? The same thing applies even for the spring oscillation. Okay, spring oscillation also, it remains the same. What happens in case of a circular motion? Okay, last part. Circular motion and projectile motion also I want to discuss. Anyway, since it is revision, because if it was not revision, we would have seen only simple cases. So we'll see all the complex cases now. This is ST graph once again. This is for SHM, and this is for circular motion. Circular. Now, in case of circular motion, what happens? How does the ST graph change?
For circular motion, it will be the same thing, kind of, right? Because oscillations, in some sense, it's very similar.
Now, we need to look at two types of circular motion. One is the horizontal circular motion. Other one is the vertical circular motion. Will it be the same for both of them? Now, in a horizontal circular motion, you have a string and you are making it move like this. It's moving with uniform velocity. Let me say this is my x-axis. This is my y-axis. Now what can happen? You are going to talk only about the x-axis. As time proceeds, now what happens? Do you get the same value here? No, you don't get the same way. Because you see, during the x-axis movement here, the velocity keeps on changing. Here, the velocity, does it change? When the particle is here, the speed, I'm sorry, the speed, not velocity. We should not talk about velocity here. The speed of the particle here, when the particle is in a uniform circular motion, when it is here, let us say this is 5 meters per second. It is trying to go like this. When it is here also, it is going like this. Here also, it is 5 meters per second. Everywhere it is 5 meters per second only, right?
Yes.
So which means the velocity is a constant here. Sorry, the speed is a constant, not velocity. Speed is a constant with respect to time. So somewhere it should be a straight line.
Yes.
Okay, and then distance. Now here, how do I find S versus T? Now we have think about it. I will also think about it. Yeah. At t equal to 0, the particle is here. At t equal to 0, the particle is here. And then as t proceeds, the particle starts moving in this direction, goes like this and comes back. Which means now we are interested only in the x coordinate. We're not interested in y coordinate here. At a given instant of time, let us say the particle is here. Let me draw a line here. Put a triangle here. Let this make an angle theta. If this makes an angle theta, then this will be your x over here. And this is the radius r here. So you can now say x equal to r cos theta. Can't we say this?
Yes.
So therefore, the value of x equal to r cos theta, initially it is somewhere over here, then it keeps on decreasing, becomes 0, and again it goes back like this, and again comes back. Now, value of x cannot decrease. Am I right?
Yes.
So value of x has to increase. Now, how do we do with it? The maximum value during one full cycle. Again, we'll do the same analysis like this. We'll start at t equal to 0. T equal to 0 here. Then let us say this is my total time period t. That means the time taken to full one circle, capital T. Then this will be my t by 2. This will be my 3t by 4. This will be t by 4. Now at t equal to 0, the particle at this point is at this point. At t equal to t by 2. At t equal to t by 4. Where was the particle? The particle is somewhere over here. And what was the distance from this point? What is the distance it has traveled from this point? I think we need to take a new slide for this. So this is my circle. This is my y-axis. I'm going to map only one coordinate, which is x-axis here. So this was at t equal to 0. I started here. Now the particle starts from here, and as it is going, it arrives at this point at a time t by 4, at this point at a time t by 2, this point at a time t by 4, and I have to graph these events as a factor of distance versus time. Yeah. So t equal to 0, it is here. Now this is t, this is t by 2, this is 3t by 4, and this is t by 4. Okay. So now at t by 4, what is the distance traveled here? The distance traveled here is pi r by 2. Am I right?
Yes, sir.
So this is 2 pi r. This is pi r. This is pi r by 2. So this is pi r by 2. Then when it reaches here, it is pi r. So I'll get one point here, other point here. Third point will be 2 pi r by 2, 2 pi r by 2, 3 pi r by 2, 4 pi r by 2. So here, fourth one will be here. Now, when I find out what is the speed at any instant, this should be a constant, which means I should get a straight line like this. Correct?
Yes.
Now look at just to verify this, just find out what is the speed, because I said uniform circular motion. Let us find the slope at any point. Let us find at this point. When I do this, the vertical distance is 3 pi r divided by 2, and the horizontal displacement is 3t divided by 4. So this goes away, so I get this as 2 pi r by t. Okay, which is 2 pi r divided by t should be the answer. Did you understand how to get distance time graph?
Yes.
Okay, this was really a complex question. I never thought of it, but anyway, so it was a way of analyzing things. Right, so we have seen distance time graphs. Then now let us look at velocity time graph. I think we have completed any other case study. Oh, I thought of talking about projectile motion, distance time graph. Projectile motion. Take a particle, throw it, comes down like this. The other particle, other projectiles you can discuss. You can think of it. Now let us look at distance time graph once again here. Now I am interested in drawing only the x coordinate here. The time taken by the particle to start from here and to reach here is capital T. Half of it is t by 2. It reaches the maximum point. I want distance here. I do not want displacement here. Yes, this will be more complicated. It's not so easy, because we only determine the range. We don't determine the path of it. Okay, I think I have taught you projectile motion. We have done projectile motion, right?
Yes.
Now, how do you arrive at distance time here? Distance time graph of a projectile motion, of a curve especially. How do you get the curve length? The question here is only about curve length. You should just say at t by 4, what is the curve length of the particle? At t by 4 to t by 2, what is the curve length? From here to here, maybe if I take one more, 3t by 4, what is the curve length here? That's what we need to look into it. Now the question is, how do I determine the curve length? We haven't done anything related to curve length. The particles, can we try out with this x equal to y, x equal to no, y is equal to x tan theta minus gx square by 2 u square cos square theta. This gives me the equation of the trajectory. But I don't want that. I want only the distance traveled. Now this will not be useful. Distance traveled by the particle. That means I'm looking at what is the distance traveled here. Total distance traveled. How do I get the curve length? I have to look into. In fact, I too don't know what is the answer for this. I have to think about it. Okay, give me some time. Let us not waste time. So next class, just remind me. I will definitely look into this. I'll answer you this question. Okay, so now we have seen distance time graph. Now let us look at velocity time graph. In the meantime, if you get an answer, just send me a WhatsApp message. Let us see. Okay, now let's just velocity time graph. Velocity time graph tells me it's a plot of velocity versus time. And then this sometimes can be a straight line. What do you mean by a straight line here? Hey, just a minute. I'm sorry, not velocity time graph. We have to start about displacement time graph.
Yes.
Displacement time graph. We'll finish up this, and then we'll go to velocity. And when it is displacement time graph, it's time, this is displacement. What does this tell me? Can you give an example for this?
So that means it's at rest, no?
It's at rest from a given point. Um, Can we also say the particle is moving equidistant from us whenever we see? Okay, let us say, okay, I want to take up a case study like this. I have a circular motion. In a circular motion, I am starting from here at t equal to 0. Can we say that, okay, how do I draw a displacement time graph for this particular thing? Now it depends upon the observer. Okay, in the previous case, in this case, the observer was at the perimeter. Okay, but here in the distance time graph, if the observer was at this point, at t equal to 0, and then you ask me what is the distance time graph for this particle, then probably the distance time graph would have been only a straight line. Do you agree with this?
Yes, sir.
Because the distance of the particle with respect to me here, when I'm the observer here, will always be a constant radius. So therefore, this would have defined the radius of the particle. But there is a glitch here. The glitch is that, okay, that's fine. That's fine. You can consider it like that. If it is only a distance, if I am not talking about the x and y coordinate, that's a glitch here. Okay, I can always say that the distance is nothing but the radius. Okay, now let us come back to this. So therefore, this will not be representing displacement time graph. Okay, so you're right that displacement time graph here is nothing but a particle which is at rest. Now let us look at the other graphs also. Is this possible?
Yes.
This is possible because when is this possible? Under what condition?
So that's possible when the object is already away from the origin and then it's coming back to the.
Yeah, it is moving towards you. Okay. When the displacement when the displacement equal to 0, what do you mean by that in this graph?
Displacement is equal to 0 means
Or I can also ask what is the meaning of the x-intercept and y-intercept?
so x-intercept will be.
Yeah, what is the meaning of the x-intercept and the y-intercept?
So x-intercept is where x has a certain value and y is 0, and y-intercept is the opposite.
Yeah, but from the situation point of view that you mentioned that you are standing at a point A and the particle is already at point B. At t equal to 0, the particle is now moving towards you. So in this situation, can you explain what are these points? What are these x and y intercept with reference to the situation? So look at this y-intercept here. This is your displacement. And this displacement gives you a t equal to 0, which means when you're about to start your timer, you understood what was the distance of the particle. The particle was at a distance equal to this y-intercept. Am I right?
Yes.
And when the particle started moving, the displacement started decreasing. And when it reached this point, now you answer the question that the particle is at this time, okay, after a time duration of, let us say, 3 minutes, for example. 3 minutes. It started from here at t equal to 0. And when it reached me, it took around 3 minutes for it to reach me. Can we say that?
Yes.
Right. Okay. So we have seen displacement time. We have looked into this. Okay, one more. Is this possible? Oh, sorry, not this one. Is this possible?
No, sir.
It's not possible. Think.
I don't know what the axis is. Yeah, it's not possible. So you're going back in time again.
It's not possible. What is the reason?
So again, you're going in the negative direction.
Yeah, you are going in the negative direction. Time travel is not possible. But this can be possible, right?
Yes.
Is this possible? Yeah, this is possible, but this is not possible. Is this possible? Displacement versus time. Is this possible? I've drawn a curve. Hello.
Hello. Yes.
Yeah. So is this possible? This curve, is it possible?
Yes, sir, it is.
It is possible. So what does it indicate?
It's an exponential proportion between displacement.
Okay. Now, how is the? Can you explain the situation?
Acceleration, sir.
Is this acceleration?
Yes, sir.
Why do you think it's acceleration?
So because there's the exponential this thing in that only.
No, the reason is because if it has to be acceleration, the velocities v1 should not be equal to v2. It should be changing. And definitely v1 should be lesser than v2. So sorry, v1, v2, all this should be in an increasing way. Let me say, for example, I take it one point here, second point here, third point here. If I want to find out what is the velocity at this point, I draw a slope here. I draw a straight line tangent here, and I will get the velocity at this point. Similarly, if you ask me what is the velocity here, I'll draw a tangent here, and I will get the slope here. I'll get the slope here. Now, let me call the slope here is m1, this slope is m2, and the third slope, if I draw here, is m3. I observe that m1 is less than m2 is less than m3. In other words, m3 is the largest one, which means largest velocity, average velocity, next velocity, reduced velocity, least velocity. So therefore, velocity is now seen to be increasing. Thus, this is a case of acceleration. Is this clear?
Yes.
Now you can put the same counter when the particle is going like this. Well, sorry, when the displacement time graph is like this. You can say here the velocity is highest by drawing a tangent like this. The velocity here is little lesser, and here it reduces like anything. So because the slopes keeps on reducing, the angles here, let me call this as theta 2, let me call this as theta 1, this is your theta 3. So theta 3 is lesser, theta 2 is between theta 1 and theta 3, theta 1 is the highest. So therefore you can say that the slope here is larger. So this is how you can rate the displacement versus time in case of accelerated motion. Okay, and then we have seen accelerated motion, we have seen particle at rest. Uniform motion is nothing but a particle's graph looks like this. Is uniform velocity motion. What else did we discuss in distance time graph? We discussed about pendulum and we discussed about SHM. Yeah, so let us do the same thing here also. SHM. I'll take another 5 minutes to finish this off. Yeah.
Yes.
Now, what about SHM?
So that's it.
So how should the graph look like here? Do I get the same graph what I had got there, or What is it like?
Same thing as pendulum.
No, you won't get it as a pendulum there. You will not get that one, but you will get a different graph there. Let me draw the graph for distance versus time. Distance versus time. You got a graph like this. You got a graph like this. 4 loops, you got it like this. Now, how does it look here? The displacement is not increasing with respect to time. So what's happening here? You start it here at t equal to 0, t equal to 0, sorry, t equal to t by 4. At t equal to 0, the displacement was x equal to 0. At t equal to t by 4, the displacement was plus a by 4. At t equal to t by 2, the displacement was 0 once again because it comes back to it. At t equal to 3t by 4, the displacement was minus a. Then at t equal to t, displacement was once again 0. Right?
Yes.
Now, how do we draw it? See, therefore, your displacement only varies between displacement. I'm sorry, this is not a by 4. I think this should be a. See, displacement varies only between plus a to minus a. But in this case, this was a, this was another a, this was the third a, and this was the fourth a. So it varied from 0 to 4a here. But here it is not so. So how do we draw the displacement time graph here? You have learned this.
Yes, sir. So
You should now ask the question, how does the instantaneous displacements vary with time?
this is the regular wave.
Sorry?
Isn't it just the normal wave which we draw?
Yeah, that's it. That's it. Okay, this is the answer for it. Projectile, I'm still not very clear. Projectile, I have to think about it. Seems to be a bit complex. Okay, now let us look at circular motion. Now what happens here? Now the question is, where is my particle? Particle is here. We did the same thing there also. At t equal to 0, it's here. And wow, this is much more complex. Oh, it is not so easy. Okay. We have to think about it really. Now, how does it change?
We have to think about angular velocity and everything. So
Sorry?
we have to think about angular velocity also.
Angular velocity. Angular velocity, we can get it. We can say v equal to r omega. Omega
Yes.
equal to v by r. Or you can say 2 pi r by t.
Yes, but it won't be the same.
No, I am taking a horizontal circle once again, not a vertical one. Effect of gravity is nullified. So here what happens is, again, let us take the same thing. This is 0. This is at this point, at this point, at this point, and again back here. At t equal to 0, it's here. Let me call this point A. This point will be at a distance of root 2r, because the displacement here is root 2r here. The displacement here is 2r. Displacement here is 2r. And the displacement here is once again root 2r.
Yes.
So I don't have this one more coordinate here. And what is it I'm doing? Oh my God, this is a long time. This is my 2r, let us say. Root 2r. So r square plus r square is 2r square, 2r square, r root 2. Yeah, root 2r is nothing but 1.4 times r. This is 1r, 1.4 will be here. This will be 1.4 times r. And now what is that we need? Time coordinate should be 0. This should be my t by 4. This should be my t by 2. This is my 3t by 4. And then this should be my t. These are the time coordinates. I'll draw an axis here. Okay, let it be like this. At t equal to 0, particle is here. At t equal to t by 4, the particle was supposed to be here. Particle supposed to be here. At t equal to 2r, at t equal to t by 2, the particle has reached this point. Then at t equal to 3t by 4, again, it has come back. 3t by 4 is what? This point, which has again come back to this point here. And then at point t, it's at this point. So it looks like a curve here.
Yeah.
It looks like a curve here, something like your sinusoidal curve. But we need to prove whether the displacement is a sinusoidal curve or not, by some mathematical means that we need to look into it. If you need to look into it, then could be okay. So this is a curve. Like this is not a straight line, because you see at every point the displacement changes. So if I take this point, this will change. Maybe we first need to arrive at an angle and then try to work it out on it. But to start from t equal to 0, okay, the angle is 90 degrees. And then slowly we have to make this tangent come down like this to t equal to theta is equal to 0 degrees. From plus 90 to 0, and again when it is going like this, we'll start from 0 to plus 90 once again, and then find out how is this distance, the displacement as a function of theta, how do you express it? When you do that, then you can easily work out with the solution. Is this clear?
Yes.
Okay, so we'll stop here. When is your next class? Friday, right? Friday, Saturday, Saturday.
Yes, yes. Fridays.
Friday. Okay, fine, Friday. Okay. So we'll have it on Friday then.
Okay. Yeah. Thank you, sir.
Yeah,
Bye.
bye.